structure. We see it everywhere we look in the universe. From the elegant tendrils of spiral galaxies to the regular orbits of planets around a star like our own, to the DNA that carries the code of life. We see again and again that nature creates larger structures from collections of just a few smaller types of components, and this creates tremendous variation. Billions of stars are organized to make galaxies. Any number of planets and stars come together to form solar systems, and so on. If we continue to shrink our scale, we see that nature continues her trend of using modular constructs of just a few simpler structures to create a truly awesome and diverse universe. In this lecture, we're going to discuss one of the smallest systems that follows this tenet. Indeed, one of the smallest systems in all of creation, the atom. It's important to start our discussion by pointing something out. Atoms actually can be divided, but doing so causes something very special to happen that doesn't happen when we divide larger samples of elements. Take the example of a bar of gold. That bar of gold can be cut in half to make two smaller bars of gold. Those can be cut into smaller pieces as well, and they're still gold. And the process can continue, creating ever smaller and smaller samples of that element, gold. But if we could continue to do this perpetually, eventually we would arrive at a point where we have just one atom of gold left in our sample. So what now? Is that atom of gold truly indivisible? Actually, no. It can be divided, but in doing so, its identity changes. The two fractions created by splitting an atom of gold are no longer gold. They're something else. But this leads us to an interesting question. What are atoms themselves made of? If they can be split into other smaller atoms, then they must be made of even smaller pieces of matter than atoms themselves. And in fact, they are. Atoms are comprised of just three types of particles called subatomic particles: positively charged protons, negatively charged electrons, and neutrons, which have no charge at all. Protons and neutrons are of nearly equal mass and reside in a dense nucleus at the center of the atom. But much smaller negatively charged electrons orbit that nucleus, balancing out the positive charge that's provided by the protons. Most of us are familiar with this depiction of the atom, but the story of how we came to understand it is every bit as fascinating as the structure's own elegance. So today, we're going to try to understand how each of these particles was discovered and how generations of scientific work ultimately came together to create our understanding of the most fundamental unit of matter, the atom. The notion of atoms was first forwarded by ancient Greek philosophers who postulated that there are just a handful of fundamental substances. Now, they combine in various ways to form all other substances. The Greeks widely believed these elements to be air, water, earth, and fire. And they also believed that particles of these elements were absolutely indivisible. Of course, today we know that none of these things are actually elements. And we also know that atoms of true elements can in fact be divided, just that they change into something new when they are. Nonetheless, the Greek term atom, literally meaning not divisible, has stuck and is still how we refer to the smallest quantity of a given element that can still exist as that element. Western discourse over the nature of matter and its fundamental units slowed to nearly a halt with the fall of ancient Greece. And it wasn't until the start of the 19th century that the concept of the atom was revived, primarily as a result of the work of John Dalton. Dalton didn't have the sophisticated scientific instruments that we do today, so he had no way to see or experiment directly on atoms. What he did have, though, was a keen intellect and the benefit of the work of Lavoisier and others. Using relatively simple observations, Dalton was able to formulate a sound atomic theory based on his observation. Let's begin by considering a couple of reactions that Dalton himself may have been able to run and observe himself. Here's a molecule of oxygen. And we're going to react that oxygen with 2 molecules of hydrogen. Now, when I do this, I create water. This is a relatively simple reaction and one that he could have run himself. Similarly, we can react oxygen with hydrogen, but instead have 1 oxygen react with 1 hydrogen molecule. And in this case, we create a different compound known as hydrogen peroxide. Now, Dalton could have made both of these, and he could have determined the masses of his starting materials and his products. So let's say that he does this. And he was able to determine that when 32 grams of oxygen react with 4 grams of hydrogen, 36 grams of water are produced. This is known as the law of conservation of mass, because 32 plus 4 equals 36. And he could similarly observe this when he made peroxide, let's say. Right? In this case, 32 plus 2 is equal to 34 grams. So consistently, when any reaction was run, the mass of all the products was equal to the masses of all the starting materials. So this is our law of conservation of mass. Now there's one more important observation that helped him to nail down the atomic theory. Notice that in this case we have 32 grams of oxygen per 4 grams of hydrogen. In other words, a ratio of 8. And in our lower reaction, we have a situation where 32 grams of oxygen are reacting with 2 grams of hydrogen for a ratio of about 16. And notice that those two ratios themselves are very simple whole number multiples of one another. In other words, you either can have a ratio of 8 or a ratio of 16, which is double that, but never in between. So Dalton noticed this and coined this the law of multiple proportions. And it's the combination of the law of conservation of mass and the law of multiple proportions that gave him an airtight argument for the existence of indivisible atoms that come together in these simple whole number ratios to create molecules. So Dalton's genius was to combine the laws of conservation of mass and multiple proportions to make an argument for the existence of atoms. It was the only possible explanation for what he saw, an argument so strong that it finally restored traction to the atomic theories of Democritus and Plato. Dalton himself said, "Matter, though divisible in an extreme degree, is nevertheless not infinitely divisible. That is, there must be some point beyond which we cannot go in the division of matter. I have chosen the word atom to signify these ultimate particles." But Dalton believed that he had reached the end of the story. In his mind, atoms were the ultimate particles of matter, and nothing smaller could exist. For his purposes, thinking of atoms as indestructible, undissectable pieces of matter worked. Now, we would have to wait another century before technology caught up with the atom, leading to the realization that the inner workings of this remarkable construct of nature depend on a complex but predictable combination of even smaller particles that we call subatomic particles. The first of these advances is one which most of us are familiar with. It has only been a decade or so since that large, heavy, nearly cube-shaped television set finally gave way to the slim, energy-sipping displays that adorn the walls of your favorite big box stores. But the technology on which these household devices of the late 20th century were based actually was devised much earlier. The cathode ray tube, or CRT as it is sometimes called, was actually developed at the end of the 19th century, and it played an important role in the advancement of human understanding of atoms. Thomson's cathode ray tube. It was a fairly simple evacuated glass tube. Now, this tube contained 2 discs, and those discs were each connected to one terminal of a battery, creating an electrical voltage across those 2 plates. The negatively charged plate would be called the cathode, and the positively charged plate would be called the anode. Now, when this apparatus is constructed, a beam of some sort can be observed traveling from the cathode to the anode. And Thomson used an anode with a small hole in the center, which allowed the beam to continue along the body of the tube. Now here, in this environment, he could study that beam. Unperturbed, of course, the beam was perfectly straight. But Thomson noted that when he placed charged plates at the top and the bottom of that tube that the beam bent ever so slightly in the direction of the positive plate. Now, this told Thomson two important things about what was making up his so-called cathode ray. First, it had to be negatively charged because the positive plate attracted it. This prompted him to name these new particles electrons. Second, and maybe even more importantly, the extent to which the beam curved allowed him to estimate just how massive each electron in the beam must be, since larger particles would necessarily be deflected less by the charged plates. Now, using that cathode ray tube, J.J. Thomson was able to create isolated beams of pure electrons and measure their mass, velocity, and charge. His measurements, though, led him to a startling conclusion. The electrons in that beam were smaller than atoms. This led Thomson to propose the first ever structural model for an atom. More than 100 years after Dalton repopularized the concept of atoms, the first real attempts to explain their structure had finally been offered. Thomson postulated that atoms consisted of the small, negatively charged electrons he had observed embedded in a very low-density, positively charged spherical matrix, making up the rest of the atom's mass distributed throughout that sphere. A sketch of his model with electrons peppered into a positively charged sphere evokes images of raisins in a bowl of pudding, earning it the moniker of Thomson's plum pudding model. But this first attempt to explain atomic structure was short-lived, as less than 2 decades after Thomson proposed his plum pudding model, his own protege, Ernest Rutherford, conducted an experiment which was intended to build on Thomson's model, but instead disproved it outright. Rutherford is credited with the discovery of what are known as alpha particles. Alpha particles are a much larger charged particle, more than 1,000 times larger than electrons, and they're created during the radioactive decay of heavy elements like uranium. But Rutherford is not most famous for discovering these particles. He's most famous for what he did with them next. Rutherford was curious to know how these relatively large, energetic alpha particles would interact with atoms as they passed through.
Atoms for kids. Look around you. See the desk you're sitting at? The clothes you're wearing? The couch in your living room? The dog or cat that might be lying on that couch? And even that healthy snack you may be eating? Believe it or not, all of those things are made up of atoms. In fact, everything in the world that you can see, touch, and even things you can't, such as air, are made up of tiny building blocks called atoms. Without these atoms, you would not exist, and neither would the things around you. Atoms are so small you can't see them, unimaginably small. But you can see, breathe, and touch the things made from atoms. Atoms make up the cells that are part of everybody's body, and the particles that make up every solid, liquid, and gas in the world. So, if atoms are so small, how do we even know they exist? They're so small, you can't even see them with the highest powered microscopes. But we do know they're there. That's because more than 100 years ago, a scientist named Ernest Rutherford was able to bounce other small particles off of atoms and witness the interaction. It was kind of like you bounced a soccer ball off a tiny, tiny super ball. The way that super ball, or in Rutherford's case, atoms, acted, told him they existed and what they were made of. This history of how atoms were discovered is a lesson for another time, but scientists have proven the existence of atoms in many different ways over the last century. They're definitely there, and they're really cool. So, what is an atom made of, and how does it behave? It's hard to believe that inside every atom there are 3 even smaller particles. These particles are known as protons, neutrons, and electrons. The difference in the way these 3 particles exist within every atom and the way they interact with other atoms help determine what these atoms create. These atoms make up wood or water or metal or anything. But we'll get to that shortly. First, let's talk about these three particles: protons, neutrons, and electrons. A proton carries 1 unit of positive electric charge. An electron carries 1 unit of negative charge. And a neutron has no electric charge. Together, the protons and neutrons make up the nucleus of an atom or its center. And the electrons spin around the outside of the nucleus in what is called a shell. How do these super tiny atoms work? And what do they do? The different ways that atoms are organized determines what they are, or what elements they make up. Elements are the building blocks of molecules, and everything around us consists of molecules. All the elements are different, and there are 120 of them. These 120 elements are laid out here in the periodic table of elements. This chart is used by scientists, like physicists and chemists, to study how solids, gases, and liquids behave. It all depends on what they're made of. You'll probably spend a lot of time studying this chart later as you continue learning about science. This is the element oxygen.
There's an old particle physics joke: don't trust atoms. They make up everything. While that's actually not entirely true, most of the stuff we interact with on a daily basis is made of atoms, so it makes sense that we all have to learn about them. And in school, we are taught that atoms are made of some combination of protons, neutrons, and electrons. The simplest atom has just 1 proton and 1 electron buzzing around it, and that is hydrogen. But it turns out that there is an atom out there that's even simpler than hydrogen. It is called muonium, and it may help researchers understand the deepest mysteries of physics. Muonium gets its name from a particle called a muon, so let's start by explaining what that even is. Basically, it's a particle that is almost exactly like an electron, with the same negative electric charge, but there are 2 key differences between them. First, a muon is about 200 times more massive than an electron, though that still makes it about 9 times lighter than a proton. And second, it is unstable. After about 2 millionths of a second, it will spontaneously decay, leaving behind an electron and other weird subatomic particles. Those 2 millionths of a second are, of course, imperceptibly short to humans like us, but for muons, it is long enough for them to interact with other particles, and not just that, but also to have, relationships with them. And that includes making something that looks a lot like a hydrogen atom. But this doesn't make any sense. If a muon is negatively charged, and hydrogen is supposed to have a positively charged proton in its center, how is muonium another kind of hydrogen? Well, it's because a traditional muonium atom doesn't actually contain a muon. I know. It's wild. Instead, it uses an anti-muon. Yes, we are dealing with an atom that is partly made of antimatter. Now, while visions of matter-antimatter explosions may have just popped into your head, antimatter is really just a different kind of matter. Every type of subatomic particle has an anti-counterpart with the same mass but opposite electric charge. An anti-muon has the same mass as a muon and it decays in the same amount of time, but it has a positive charge instead of a negative one. And here's the key point. The strength of that positive charge is exactly the same as the positive charge of a proton. So if a regular old electron is in orbit around an anti-muon, that is a muonium atom. Those things don't annihilate each other because they're not each other's matter-antimatter counterpart. And when it comes to chemistry, the difference in mass between a proton and an anti-muon doesn't matter nearly as much as their identical electric charges do. So an atom of muonium, ignoring its super short lifespan, acts as a chemical in almost the exact same way that a proton-based hydrogen atom does. This is why some scientists consider muonium to be the lightest form of hydrogen. And just like other forms of hydrogen, like deuterium and tritium, chemists gave muonium an honorary chemical symbol, Mu. Now, if you prefer to think about muonium as its own element and not like a quirky kind of hydrogen, that could make muonium the simplest element in the universe. Just like muons, antimuons are fundamental. They are as simple as a single subatomic particle can get. Meanwhile, an individual proton is complicated. It's not fundamental. Each one is made of smaller particles called quarks. So even if the simplest hydrogen atom only has one proton and one electron, muonium is even simpler. These days, antimuons are actually fairly easy to create in particle accelerators, although they come out traveling pretty quickly, so making muonium requires taking a concentrated beam chock full of antimuons and then slowing them down. This can be done by literally putting aluminum or gold foil in the beam's path, which slows the antimuons down by making them bump into electrons and the like. When they get nice and slow, the old adage of opposites attract kicks in. The positively charged antimuons can peel off some of the negatively charged electrons orbiting other atoms to make a bunch of muonium. Now, physicists are not making all of these exotic atoms just for fun. They want to make muonium because it lets them use experimental techniques from the well-developed field of atomic physics to study our murky subatomic reality. For instance, each kind of atom has a unique sequence of colors that it emits and absorbs. It's called a spectrum, and it basically is a barcode that lets scientists learn more about the subatomic structure and properties of a given atom.
H.G. Wells, who first imagined time machines and alien invasions, had a nightmare of a future world where atoms were weaponized. In his book, called The World Set Free, written in 1913, he coined the phrase atomic bombs and loosed them on helpless civilian populations. He said his vision of a nuclear war between England and Germany in the impossibly distant future of the 1950s. In 1933, the Hungarian physicist Leo Szilard was contemplating becoming a biologist.
Dr. Szilard? Are you quite all right in there?
He read Wells's novel, and it started him thinking. Szilard knew that atoms are made of protons and neutrons on the inside, and a skittering veil of electrons on the outside. Suddenly, while waiting for the light to change at this intersection in London, he was struck by the thought. If he could find a sufficiently large amount of an element that would emit 2 neutrons when it absorbed 1, it would sustain a nuclear chain reaction. 2 would produce 4, 4 would produce 8, and so forth, until enormous amounts of energy in the nucleus itself could be liberated.